I try to be careful with my money. But I'm not afraid to go into a casino because I try to use my head there. But let me sort of tell you how I'll let you decide if I've actually gained an international reputation as a gambler. So how did my story start? So many years ago, Emory College decided there should be a thing called freshman seminars. That we had to have these small classes for students, and they should be on topics that were not typical topics from the departments. At the time, I had been teaching advanced placement calculus for several years, every fall. The students were fine, but they were boring to me because they didn't have much energy. They didn't really understand how they could use this later. And so what they really wanted was a two-step algorithm to do everything. Unfortunately, the world doesn't work that way. Two-step algorithms are rare. They're hard to come by. Well, because they bored me, even though it was an easy class to teach, I decided I would try to create something that was more fun. So I sat down and said, what would I want to do if I was a student? And I decided I would create this course called Mathematics in Games, Sports, and Gambling. Well, I created the course, Emory College bought it, said fine, and so I taught it for over 20 years. And I'm proud to say there was never an empty seat, and no student ever dropped. And they didn't all get A's. And most of them had a good time. And they learned to appreciate something about mathematics that they'd never seen before. That it applies all over the place, if you look. So in the course of today, I'm going to tell you a bunch of stories about things that happened to me because of deciding to make this course. But I'm going to show you a few of the problems that I would present to the students. And we'll see how well you handle them compared to freshmen. So this is a math talk. There will be a test. Okay? So that's pretty much how my story begins. So where did I make my mistake? Well, after I taught this course a few times, I got a request from the Wheel. They wanted to come in and observe the class once and write a story about it. I should have known better. I had dealt with the Wheel before. They had interviewed me before. And the story that they wrote after they interviewed me bear no resemblance to what we had talked about. And I knew that, but I figured, come on, it's just a little campus newspaper. Even if they write stupid things, it doesn't matter. So I'll say yes. So the student came, and he came on a day when I was teaching fundamental counting. You would think to yourself, well, counting is easy, 1, 2, 3, 4. No, counting major things is hard. And there's an old mathematical joke that there are 3 kinds of mathematicians. Those who can count and those who can't. And it's because real counting is difficult. The first step towards this is to decide on what you're counting, if the order in which you're counting things matters or it doesn't. So there's a chapter in a book that I've written called Batting Orders versus Poker Hands. Order matters in a batting order. If you bat out of order, that hitter's out. It matters. But if you're dealt 5 cards, it doesn't matter what order they're dealt to you. It's the 5 cards at the end that matter. You have to count those things differently. So the day before the Wheel reporter came, I had laid out this to the students. And the day that the reporter came, we were going to count how many different 5-card poker hands there are of each type. Right. Straight flush, full house, etc. down the line. We're going to count these. And if you count them, you actually understand why they're ordered the way they are. The fewer possibilities are the higher ranking hands. It makes perfect sense when you see it. But counting some of these isn't so easy. I'm not going to make you count any of them. Okay? Well, the student came, he sat there, never asked a question of me. Lecture was over, he left. The next wheel came out. I ran down, picked up a copy, sat down and read it. And I read this story about this unbelievable poker class where I was teaching them everything about poker. I never mentioned one word of poker strategy in that lecture. There's no place for it there. It's all counting. It's all math. There was no mention of mathematics in the wheel story. And I read it and went, I get what I expected. That's okay. And I didn't think anything more about it. We'll come back to that in a little bit. Now, I know you're at the edge of your seat saying, how can he prove he has an international reputation as a gambler? Is he going to take me to Monte Carlo? That would be great. I've never been to Monte Carlo. It would be great. But here's an email I got at the beginning of January. Dear Mr. Gould, we ask you to give an interview today or tomorrow and answer a couple of questions for our program via Skype to talk about how to use math to win gambling. Is it possible or not? Is it possible or not to use math to win at gambling? Or is it possible or not for me to do the interview? It's not clear. Even I can grade that English. And if you'll notice, there's a Russian email address on the return. Russian TV wants me. I don't want Russian TV. She offers me nothing. There's no incentive. She's snapping her fingers. We have to do this today or tomorrow. I'm bad at taking orders. So I turned them down. Yeah, well, there's nothing in this for me except disrupting my schedule to suit them. So I said no. You decide if I have an international reputation. I'll prove it even further later. All right, your first pop quiz. Here's a game, a really simple game. A man has 3 cards. I'm the man. Here's 3 cards. A card that's red on both sides. A card that's blue on both sides. And a card that's red and blue. Okay? So the game is, I will put these in a hat, scramble them up, and I'm going to pull one and show you one side, and you guess the color on the other side.
Ron, was your presentation on this?
Yes.
Okay.
And I guess, okay, should I say what I'm looking at?
Yeah, she's looking at.
I'm looking at a red card, red side. I'm going to guess red on the other side.
Very good.
Total accident. No logic.
We'll try it again then. Scramble them up. I pull a card. Oh, a blue side this time. Vernon, guess.
Blue?
Wrong.
Yeah.
Okay. So if you think about this, there's 3 cards, there's 6 sides. 3 of the sides are red, 3 of the sides are blue. I show you a side, you guess the other side. Is this a fair game? If I was to try to bet you even money to play this game, would you be happy to do it?
No.
Well, if you were one of my students, you would immediately say no. And you would immediately say, no, there's no such thing as a fair game, or you wouldn't be interested in it. And that's right. Okay. I am not interested in fair games. I am interested in games that give me an advantage. Right? So, is there a strategy for one of the players in this game is the question. The answer has to be yes, or I wouldn't be asking it. So then my students catch on to that part pretty quick. So which player has an advantage, and what should they do?
The one who goes first. Wouldn't the one who goes first have an advantage
Goes first in what?
in the picking of the color?
No. It's the person who guesses the color has the advantage. And why? That's the question. Why is there an advantage?
Because you've eliminated one of the 6 possibilities.
That's kind of it, but if you did that, most people guess the other color. And I claim the proper guess is the same color all the time. And the reason is 2 out of the 3 cards have the same color on both sides. And everything's decided once the card is picked. And 2/3 of the time, it ought to be a card with the same color on both sides. So I would be happy to play somebody even money if I was the one guessing. And I'd be happy to play the game over and over until I cleaned out their wallet. Okay? Clear to everybody? Pretty simple once you think about it. Okay? That's all the props I brought for today. All right. Where did I put? Okay. So that's what this is supposed to do. So let's try a different game here. Actually, maybe I'll tell you another story first. Yeah. Before we go on to this game. So when did I get a clue that something had happened to my reputation? Well, I was sitting in my office after having taught the course for a couple of years and having this wheel article out. Sitting in my office one afternoon and the phone rang. Well, it rang fairly regular. Picked it up, said hello. And the person on the other end told me that they were an Alabama lawyer and they would like me to be an expert witness. And I said, okay, explain. And he said, well, he had 2 clients who were arrested for running a Texas Hold'em poker game. And I said, okay, what does that have to do with me? And he said, well, the law in the state of Alabama says that if it's a game of skill, pure skill, it is all right to bet on it. But if it is a game of chance, it is not. And I want you to testify that Texas Hold'em poker is a game of pure skill. And my response was, so you want me to perjure myself? And he said, no, it's a game of pure skill. And I said, no, there is skill involved. There is no question that any poker game has some skill involved. But any game in which cards are dealt has a chance of randomness and therefore blind luck to the unskilled. And any mathematician who would testify otherwise is perjuring himself. And I don't think you're planning to pay me enough to get me to perjure myself. He agreed with that statement. And we concluded that I would not be the expert witness. So when he hung up, I sort of thought to myself, why in the world would he even know who I was? Why would some Alabama lawyer know me? And then I realized what had to have happened. The Wheel put their article online. And since I taught a poker class, I was the expert. So this was the start of things happening. All right, let's try another game. Here's a 3x3 chessboard. There are 2 blue knights in the top row and 2 red knights in the bottom row. Everybody know how knight moves in chess? Sort of an L shape, either 1 up and 2 over, or 2 down, 1 over, etc. So the game, or the question is, I want to know if it's possible to take legal moves only and get the 2 blue knights down in the bottom row and the 2 red knights up in the top row. Hint, I asked the question, of course it's possible. So the real question is not, is it possible, but if it can be done, what's the minimum number of moves that it takes to do this? That's the mathematical question. Any guesses?
I don't see any hands.
Are they alternating turns?
Doesn't matter. Move any knight whenever you're in the mood, just as long as it's a legal move. It's got to be more than 4. 8 is the typical answer, and 8 is wrong. But 8 is the answer that I always set everybody up for. 16 is the right answer. 16 is the right answer, but how do I prove that 16 is the right answer? Right? To say 16 is the minimum, why not 14? Why not 12? Got to convince me those aren't the right numbers. That's often the hardest part of some of these mathematical problems, is showing that it's not possible. Possible is easy, just do it. Not possible is harder, much harder. Okay, so as a mathematician, I would look at setting up a model, something that I could control and deal with for handling this game, this puzzle. So think of putting a dot on every one of the 9 squares of that 3x3 chessboard. And now, an edge like this between these 2 dots says that if the knight is here, he can move to there. So each of these edges demonstrates a legal move from one square to another. So this is the whole game. Everything about this game is captured right here. So if I can analyze this in a reasonable way, I have a chance of figuring out what's going on in this game. This kind of structure is called a graph. It's not the graph you graphed in high school. It has nothing to do with that. But it is the kind of structure I deal with as a mathematician. So I'm a graph theorist. I'm an extremal graph theorist, which means that I tend to push parameters as far as I can to determine properties. Hint, if you are an extremal graph theorist, never tell a TSA agent you are an extremal graph theorist if they ask what you do, because then you're up against the wall. Extremal something or other is bad. I've been there. Okay, so we look at this model of the game, and we have to ask, how do I analyze it? Well, I'm going to take it apart a little bit. If I redraw it, it looks like that. Okay, to try to convince you, A goes to 1, 1 goes to D. A goes to 1, 1 goes to D. If I check that all the way around, this is the same graph, just drawn where I can see it better. That's the nice part about these. Most of the time in the questions you're involved with, you can draw them any way you want if it helps you see what's going on. Okay, so now let's analyze this. Let's suppose we first decide to move blue knight number 1. He can go here or there. It's a symmetric picture. So I'm going to choose that he goes to the square one. Once that choice is made, everything else is fixed. Red knight number 1 can't go here because blue knight is already there. And this is not killing him, this is just moving him. So that says that red knight has to go this way. Well, if red knight has to go this way, then this red knight has to go to 3. And this blue knight has to go to 2. They're all fixed once that first direction is chosen. Okay, well, let's go back again. I want the 2 blue knights to end up on C and D, and the 2 red knights to end up on A and B. That's where they started. Okay, so if blue goes here, he has to get down. He can get to D here, but he can't stop, because that won't get this guy where he needs to be. So in fact, he has to go here, that's 2 moves, and here, all the way to C, in order to create enough space for this guy to get to D. Is that clear? All right, well, blue knight number 1 needs 4 moves to make it possible for blue knight number 2 to take 4 moves to get where he needs to be. Same applies to the reds. 4 knights, 4 moves each. Seems like 16 to me. And that, as far as I'm concerned, is a mathematical argument that says 16 is the best you're going to do. Okay. First time I showed this to my class, they went, "Wow, give us another one." That's all you ever want as a teacher, is to get that kind of reaction. And I gave them a different one, but I'll spare you that one. Okay, next story. The next thing that happened to me was I received another email from an offshore website inviting me to write articles about gambling. Doesn't tell me what kind of article, what they're hoping for, anything about it. So I went and looked at the website. And it was very much a pro-gambling website. Now, did they offer me any money? They just wanted me to take time, write some pro-gambling article of any kind, and stick it on their website. Guess what their answer was? No. Not likely. Not likely. Especially since, at the time, Steve Sanderson was the dean, and he kept telling me, "Don't you ever promote gambling in that class?" I said, "I don't. I do math. Decisions they make about gambling after that are their own. Some decide, and some have told me repeatedly, I'll never gamble now that you've shown me what's going on in the casinos." And others say, okay, now I got an advantage. I can't control how they think. I just present mathematics. Okay. This is Sir William Rowan Hamilton, renowned mathematician. He was still an undergraduate when he was appointed the Royal Scholar of Ireland. His name appears in several branches of mathematics because of his contributions. His contribution to this talk is very, very little. But after looking at him for a little while, I start to look better. He was kind of a grumpy guy, renowned drinker. I have to admire him for that he could do what he did and drink as much as he was renowned to have had. Semi-impressive. All right, let's play with the chessboard again. Here is a standard chessboard, 8 by 8. Okay. There's a domino. And here's a trivial question. Can I cover up the chessboard with dominoes so that no domino is half on the chessboard and half off the chessboard, and everything in the chessboard is covered. This one's trivial, folks. Yes.
Seems like yes, yeah.
Of course. I lay 4 across each row and I'm done. Okay, so that clearly isn't the question of interest. Okay. If I cut, just for the moment, just the upper left corner out of the chessboard, now can I cover it perfectly? Well, of course not. Now there's 63 squares left, and to cover with 2 square dominoes means I need an even number. So that's out. So now let's cut out the lower right-hand corner as well. Now I got 62. 62 squares. Can I cover it perfectly with the dominoes? I hear yes, and I hear Pardon?
You cut out 2 whites.
I cut out 2 whites.
You need a black and a white for it.
Bingo. Give that man a silver dollar. Every one of those dominoes has to cover 1 white square and 1 black square. And I took away 2 white squares. So you can't do it. That's a good observation. Excellent. I like talking to smart people. It's good. Okay. So let's change the question slightly. So there's that, and there's the 2 white squares missing. But here's a theorem due to a person named Emory that says if I remove any 1 black square and any 1 white square from the 8x8 chessboard, then I can tile the remaining board with 31 dominoes. Tiling means this perfect covering. Okay? First time I heard this theorem, I went to a thing called MathSciNet, into the math database to look up Emory. He isn't in there. Even though there's this thing called his theorem, he never published it. I then went further and figured out that Emory ended up being a computer scientist. Just one with some good mathematical sense. They don't all have that. Okay, so how did Emory actually prove that it didn't matter where you cut these 2 squares out, as long as 1 was black and 1 was white, that I could then do the tiling? Here's where Hamilton comes in. I replaced every square again with a dot, a white dot if it was a white square, a black dot if it was a black square. Ooh, walking in front of that blows your ear off. And then I drew lines, edges again, where I could possibly lay down dominoes. So if I just place a domino somewhere on this and follow this pattern with the remaining dominoes next to each other all the way around, I will cover the entire chessboard. This is one of many ways this can be done. Okay, is that clear to everybody? All right. I got another graph. I have a graph that we call a cycle because it starts, and if you trace it around, you can stay on it the whole way and get right back to where you started from without ever repeating anything. Cyclic. In fact, it covers every one of these points, and in graph theory, that's called a Hamiltonian cycle because Hamilton invented the idea many, many years ago. Not on purpose for graph theory. He invented a stupid little game where he took a dodecahedron, put nails in the corners, and tried to sell that in a piece of string. It said the game was to wrap the piece of string around the nail, go nail to nail, never repeating a nail, and end up back where you started. He didn't make a lot of money on that game. Hasbro wouldn't touch it. Okay? It's probably why he started drinking. Anyways, this picture is essentially the proof that Emory needed. Now, when I was an undergraduate, my instructors always said you can't prove anything with a picture. They were wrong. So let's take it with an easy example. Suppose I remove this white one and this black one, two that are adjacent to one another. Well, that just essentially takes one domino out of the tiling, right? So it's certainly tileable from there. Just follow the rest of the pattern. So that's the trivial case. So let's make it more interesting. I'm always in your way here. I'll try to bounce around. Suppose I take out this bottom black one and this top white one. They're certainly not connected. There's no one domino that covers them. So what am I left with? Well, I'm left with this piece that starts with a white one and ends with a black one. And I'm left with this other piece that starts with a black one and ends with a white one.
It's not showing up. Your pointer.
Pointer isn't showing up?
I think it's too light.
Oh, yeah.
Sure, I'll get it. Here you go.
All right, so here's a piece that, you see it now?
Yeah.
Try the top of the screen instead of the bottom.
Okay.
Yeah, yeah.
For those in the back, in the 50-cent seats. So if I take out this one and the bottom black one, I'll be left with a piece that starts here, just follow it all the way around, still a continuous piece, until I get to here at the bottom with a white one. Starts with a black, ends with a white. So what's left on the side starts with the black up here and ends with a white down there. That says that each of those contains exactly an even number of squares. It starts in one color and ends in the other. And they alternate along the way. Has to be an even number. Okay? That says I can tile each of the two pieces because they have an even number of blacks and whites, exactly the same, and it's all connected in each piece. The argument's the same no matter where I pull the 2 points, one black and one white. I end up with two pieces of even length. And that's the mathematical proof that Emory came up with. Great observation. And this, my guess is he did this as a student. Whether it was undergraduate or graduate, I don't know. My guess is probably undergraduate. And it impressed his professor so much that years later, in an article he wrote, he put it in and called it Emory's theorem. I wonder if Emory actually knows. Like I said, I couldn't find him. I've certainly never met him. But he's got a nice observation. Okay. Now my favorite story. Where are we time-wise? So I got loads of time. Again, I was sitting in my office one day. Phone rang again. I should know not to pick it up. When I was chair, I used to unplug my phone because it was much nicer. But anyways, I picked up the phone, said hello, and a female, heavily Hispanic voice said to me, "Professor White?" And I said, "No." She said, "Yes." I said, "No, that is my title, not my name." She said, "Doesn't matter, you come give seminar." I said, "Oh yeah?" She said, "Yeah." So you come Monday. This was Thursday. "You come Monday." I said, "Where?" She said, "Bogota." I said, "Bogota?" She said, "Uh-huh." I said, "And what do you want the seminar on?" She said, "You give 2-day seminar on gambling." So I'm supposed to put together a 2-day seminar in just a couple of days and fly to Bogota and present for 2 whole days. I said, "I don't think that's possible." She said, "The syndicate will be upset." And now I'm thinking, who in Bogota has enough money to be thinking about a casino, and in fact it turns out to be opening a casino, and do I ever really want to deal with these people? And my answer to that was, no, I wouldn't even deal with them in the US, let alone in Bogota. The next day, so I turned her down, and she just kept begging for a while, and she said, well, you come 2 weeks. No, I'm too busy, can't do it. The next day I got another call, this time from a woman who spoke perfect English, apologizing for the call the day before, and telling me that the cartel that was trying to start this casino really needed some advice. And I said, just hire any mathematician in Bogota who knows basic probability. Or better yet, just copy the games in an American casino. They've done all this. They have guaranteed that every game is in their favor, with the exception of blackjack, which is mostly in their favor for people who don't understand. And she said, you sure you won't come? I have yet to hear an offer. You want me to come to Bogota and work for 2 days? I don't work for free. And I'm sorry. Even when my parents as a kid told me to mow the lawn, I said, I don't work for free. Now you got to negotiate. So I eventually turned this down, and to this day, I'm not sad. But I was trying not to laugh while she was talking to me because it was kind of a funny offer. Okay, let's move on. Here's another game. Very simple game. Suppose I have 10 coins laid out in a row of various denominations. And if you sum up all 10 coins, the value is some number t, but t is an odd number. Okay? And there's a game. The game is the following. 2 players will alternately pick a coin from this row. But they can only pick a coin that's on the end of a row. They will alternate turns until all 10 coins have been selected. Each of them will have 5 coins. The one who has the biggest sum wins and gets the coins from the other person. Okay? Clear? Simple game, right? Is there a strategy for winning this game? And of course, by now you know the answer is yes, or I wouldn't be talking about it. So is there an advantage to one of the players? And if so, which player? First player does have an advantage. But why? Well, that's not quite. Well, he has the option, and that's the key. The option is the key. But how does he decide which end to choose from? That doesn't necessarily mean it's going to work.
Oh, yeah?
Well, that's kind of the idea. But how does he do that? And the way he does it is the following. Think of the coins in a row. I'm sorry.
Oh, don't worry about it. I can kick around.
But I can see it here. And now I want to think of them as partitioned into 2 parts, alternately. So I'll have 5 white coins, every other one, and 5 red coins, every other one. So before the first player selects, what he should do is quickly add up in his mind the sum of one of these 2 colors. Doesn't matter which one. He'll know if he got more than half of T or not in that color. If he got more than half of T, that's what you want to be the winner. So he will know which color he wants to pick. So let's suppose it's white. The white coins have more than half in them. So those are the coins you want. Now, I guarantee he gets every white coin. Now, how does he do that? He picks the first white coin. He has to pick this end. That's his choice. As soon as he does that, that's what's left. His opponent has to pick a red coin. Oh, that's perfect. Well, it's totally cute. Whatever red coin your opponent picks, he opens up a white coin for you. You take that one, and he's back to having 2 red coins on the end. You play it all the way through, and he wins. Now, the first time I was told this game, it was at dinner at a conference by another mathematician. I didn't immediately see the idea. And he said, don't worry about it. I'll make you feel really bad. I showed this to an 8-year-old kid, and he got it immediately. I said, good for him. Now I'll use it from here on. Once you see it, it's really simple. You just have to see it. 8-year-old kid, wow, he really wanted to hurt me. And there we were, having a pleasant dinner up till then.
Ron, let me ask a question. The reason that you said the sum, it was an odd number.
Was to guarantee there would be.
Right, so
Yeah.
there would be even, yeah.
I want to guarantee there's a winner.
Yeah, okay.
So, and it's easy. Pick 10 coins. You can easily make them come out to an odd sum. Please always feel free. Ask a question anytime. That's what I'm used to from classes. Okay. Different game. Before that, one more story. Sitting in my office again. A big mistake to go there, apparently. But this time it was an email. I got an email from a Harvard law professor saying that he was going to hold a workshop. He was inviting known gamblers, mathematicians, lawyers, and one former Supreme Court justice. And they were going to meet at Harvard, and they were going to work out a strategy to promote legalized gambling in America. Now, I didn't really care that to promote legalized gambling. It existed all over the place anyways. He just wanted it spread more, I think, to Massachusetts. And I was intrigued by the potential list of people that he had there. So I thought long and hard about it. The problem was he was going to hold this 2-day seminar right in our finals. And being a dedicated idiot teacher, I decided I couldn't actually go to this. I had to actually do my final and get my grades in. So I missed out on that opportunity. But again, the only way this guy, I had never heard of him. The only way he could have heard of me was to do some sort of web search. Thank you, Wheel. All right, new game. This is a paintball game. And there are 3 players. There's Matt, the mathematician. He doesn't play a lot. He's not a good shot. He can hit what he's shooting at about 50% of the time. There's Phil, the physicist. He's better. He can hit his target 75% of the time. But then there's Ed, the engineer. And this is his life. He plays paintball all the time, and he never misses. He hits his target 100% of the time. And they're going to have a 3-way duel, which some people have started to call a truel. But it just sounds stupid to me, so I don't. And because of their difference in abilities, they're going to let Matt shoot first, Phil shoot second, and Ed shoot third. And whoever's left after they try to kill each other off is the winner. Okay, seems simple enough, right? So the question is, what should Matt's strategy be? He's clearly the worst player. He's clearly at a major disadvantage. So what should he do?
Shoot it.
So Matt gets the first shot, Phil second, Ed third. Should they need another round, they go again. So if Matt shoots and hits Ed, okay, could happen half the time, then there's a 75% chance that Phil takes him out. So he has essentially a probability of 1/4 of winning this game. If he shoots Phil and even hits him, he's dead immediately. That takes him out. He has 0 chance of winning this game. He could surrender, go to a bar and wait for the winner to join him. It kind of makes sense. He doesn't get shot by paint and he gets a drink. Seems reasonable. But his best move is to purposely miss. Right? If he purposely misses, then Phil shoots next. Is Phil going to worry about him? No. Phil's going to worry about Ed. So 3/4 of the time, Phil kills Ed. 1/4 of the time, Phil misses. Well, Ed immediately kills Phil. Now it's 50-50 for Matt. Or Matt misses and Ed kills him and Ed wins. Well, if you do the computations, Ed's only going to win 1/8 of the time under this strategy. The best shot suddenly has a lousy chance of winning. And all he has to do is purposely miss. Now, we build a similar tree. These are called trees in graph theory. And analyze what happens along the way. This tree is actually infinite because there's a chance that Matt and Phil miss every time. So things just keep going on and on. But the numbers are written in such a way that there are what are called geometric series, and they have finite sums. So you can actually compute the probability. If you do this, and I'm not going to go through all the math and bore you with it, but you can compute that Matt has a probability of winning of 0.554 if he purposely misses. Suddenly, the lousiest player has better than half a chance of winning. If they play this over and over again, he should win more than half the time. Well, winning more than half the time seems pretty good if you're the lousiest player. The Falcons should be so lucky. Sorry. I'm just bitter. Okay? Now, without having actually computed the math for you, that's the fundamental idea here. All right. What else is on my list here? Right. So along the way, over the years, I started to get strange requests from all over the world, besides the ones I've told you about. Somebody would write me an email and saying, here's a game I invented, blah, 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 and tell me some elaborately crazy game, and say, figure out the probability of winning and let me know. And I would write back that my consulting fee was $250 an hour, 2-hour minimum. And they would say, never mind. And I would say, good, because your game was stupid. But their intention always was, have some game where there was an advantage to the house and sell it to a casino. Most of their games were so ridiculously elaborate that they would have had to pay me several $1,000s bare minimum to compute the probability. They were that crazy. But nobody was ever willing. All he needs is one sucker. One customer. Anyways, let's move on. This is my favorite mathematical card trick. I absolutely adore this trick. It was invented by a guy named Fitch Cheney, who I've never met, back in 1950. And it's a two-person mind-reading trick. Okay, that's the way you play it. So you take a normal deck of cards, you shuffle them up, and have somebody deal you 5 cards. Okay, normal 52-card deck, no tricks here. No marked cards, no nothing. Just a regular deck of cards. When you receive the 5 cards, you lay them out, 4 of them face up, and 1 of them face down. And now you call in a partner who hasn't been anywhere near you. And you say to the partner, "What's that card?" Exactly what is that card? I want to know its rank and its suit. Exactly.
Because you know, you looked at it before you.
Oh yeah, I looked at it.
Yeah, you know what it is.
But I will even leave the scene and have no contact with the person who would come in, and they could still do it. The first time I saw this trick was at a party. A mathematician friend of mine had me deal him the 5 cards. He laid them out and called his 8-year-old daughter over and said, "Anne, what's the card?" And she went, "It's the 7 of clubs. Can I go now?" He turned over the card and it was the 7 of clubs. And she was allowed to go. And it was clear she had done this trick several thousand times and was pretty sick of it. So now the question is, how's it done? You've got 2 pieces of information that need to be transmitted to the person who comes in. They need to figure out what the suit is and what the rank is. Okay? Well, easy question. If you're dealt 5 cards, what can you tell me about the suits? Bingo. 2 of them, at least, have to be in the same suit. There has to be a repetition. Mathematicians call this the pigeonhole principle. Discrete mathematicians are nice. They don't cut their pigeons into fractions. Okay? If the pigeon comes, the whole pigeon goes into the pigeonhole. So if we have 4 suits and we deal 5 cards, 2 of them have to come out in the same suit. So now you and your partner can have ahead of time a position card where 1 card in that suit will be face up, the other face down, and it'll be in a position that your partner recognizes so they immediately know the suit. So let's make it easy. Here's the suit card in the very first position. So now we know this is a club. Okay, but the problem is, which club? There's 12 other clubs. It could be any one of them at this stage. So somehow, with the remaining cards, we have to find a way to indicate the rank of this card. Well, using just these 3 cards, I don't know how to do that. 3 cards, I can lay them out in any of 6 ways. That's the number of permutations of 3 things. 3 choices for this card times 2 choices for that card times 1 choice for that card. So there's only 6 ways to lay them out. And there's potential 12 other values. So I got to cut that out somehow. I got to get it down so there's only 6 choices. Then I can use the arrangement of those 3 to tell you what that choice is. So that's That's the cryptography that's going on here. We're trying to encode information into these cards so that an 8-year-old girl can come over and go, ah, and tell you what the card is. Now, how do we do that? Here's 6 permutations. So I have no way of knowing what those 3 other cards are going to be. So I can't count on their exact values. All I can do is think of them as a low-valued card, a medium-valued card, and a high-valued card. And now there are 6 ways to do the permutation of low, medium, high. Low, medium, high, we're going to call this number 1. Low, high, medium, call that number 2. Medium, low, high, call that number 3. Medium, high, low is number 4. High, low, medium is number 5. High, medium, low is number 6. Okay? Mathematicians call this a lexicographic ordering. You've seen it your whole life. You just never called it that. If there were still phone books, and you opened one up, this audience should remember phone books. It strikes out in classes with freshmen now. The phone book is a lexicographic ordering. That's it. We're alphabetizing according to a rule. Well, here's our rule. Low comes first, medium comes second, high comes third. So it's the same thing. Okay, so it's easy for somebody to recognize the ordering of the other 3 cards and pick one of these and pick the appropriate number that goes with it. Now you should be asking me a question here. Bingo, that's the question. Thanks, Sid. Okay, we're going to break ties based on suits.
Oh,
What ordering of the suits?
club, diamond, heart, spade, close.
Clubs, diamonds, hearts, spades. Bridge players know that is the ordering. Everybody else can think of it as alphabetizing the suits. Putting them in that order. So ties are broken based on the suits. So if I have 2 of the same, the lower ordered suit comes before the higher ordered suit. So now it doesn't matter what the 3 cards are. I can figure out a low, medium, and high and make this arrangement according to the number I want to present. So the question is, why can I get away with 6? That's the key issue. No, no other cards. That's it. Everything's here. And the answer is, I want to think of the cards like a clock. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and back to Ace. Okay? When I get the 2 cards in the same suit, let's suppose I had a 4 and a 9 of the same suit. Well, then it's 1, 2, 3, 4, 5 steps to go from the 4 to the 9. I can convey that information with these 3 cards if I want to, because a 5 is possible. But 9 to 4, if I go 9, 10, Jack, Queen, King, Ace, 2, 3, 4, that's too many. And I'm always going to think of this clockwise rotation of this wheel so that my partner does the same. Okay? This is the key. So when I look at the 2 cards of the same suit, I determine which of the 2 I can count and get from one to the other in at most 6 steps. And no matter what 2 spots are picked on this wheel, one of the directions is possible with 6 or less. Always. Because there's only 13 here. And you're pinning 2 of them down. So the gaps are going to be at most 6 for you. Okay? So when this 8 was laid down, it was intended to be more than just a signal for the clubs. It was also the start of where you are on the wheel. Okay? Now, we have a 10, a jack, and a 5. That's the medium card, the high card, and the low card of the 3. Oops. What did I say? It was the medium, high, low. Medium, high, low indicates a 4. So now we come back here. Whoops. Too many buttons. We start at the 8, and we add 4. 1, 2, 3, 4. So that says that this card should be the queen of clubs. Okay, is that signaling system clear?
Why is the mystery not a time?
Because we had already decided that this first card would indicate the suit.
You have to pick, when you get to 5 cards, you have to have 2 that are the same.
There's 2 in the same
So
suit.
there had to be 2 sets because you've got 2 hearts. You just chose to use the club.
Right. In this case, I chose your choice is free.
Right.
It could be all clubs. Then it's really easy. But in this case, there were 2 different suits. I had a choice. I picked the clubs. So this position said we're going to be in clubs and we're going to start at the 8 on the wheel. This ordering says add 4, which gets me to the queen, and it's the queen of clubs.
I thought you said 7.
Oh, that was the example of the little girl.
That was just a 48-year-old.
That was the example of the little girl. It's not this example. Sorry, I shouldn't have used clubs. Redact that and put in the ace of diamonds. Okay? Is it clear? Now, the first time I showed this to students, some of them go, see, that's great. And some of them go, how am I ever going to learn those 6? And I go, how many things have you memorized in your life already? Take 2 minutes and learn the 6. And then they come back the next day. Some of them would go, I made $50 in the door last night. And I would go, and they would go, thank you very much. Okay. Where am I time-wise?
Oh, you've got 20 minutes to 1 o'clock.
All right, new game. It's a game called Penny Ante, because it was invented by a guy named Walter Penny in 1969. And here's the game. You ask your opponent to select any pattern of heads or tails of length 3. Any pattern they wish of length 3. You then select a different pattern. And we're going to flip pennies, nickels, dimes, or quarters, doesn't matter. I prefer silver dollars, but that's okay. So we're going to flip pennies repeatedly until one of the 2 patterns occurs consecutively. 3 straight tosses gets one of the patterns. The person with that pattern then wins whatever they bet. Okay? Is it a fair game? You know the answer. I'm not interested in fair games. Okay? So the question is, who has the advantage? The person who picks first on the pattern or the person that picks second? Most people say the person who picks first because they have the choice of everything and the other person doesn't. And that's, of course, the wrong answer since I supplied it. Okay, the second person has an advantage. Let me give you an example of why. Let's get to this. So suppose, just to make this really easy, your opponent picks heads, heads, heads. They want to see heads come up 3 straight times. All right, so what am I going to pick? I'm going to pick tails, heads, heads. Now, why?
The first, you already got your first already.
Well, nothing's been flipped yet.
Well, no, but it will be when you is.
This is the reason, yes. So what could happen? Well, heads could come up on the first 3 tosses, and I lose. That's probability 1/2, that's probability 1/2, that's probability of 1/2. 3 in a row, you multiply those numbers together. There's a probability of 1/8 that I lose on the first 3 flips. 1 time in 8. Otherwise, heads has to come up in the middle someplace. But before heads can come up in the middle, as was observed, tails heads has to come up first. So that says I win every other time. 7/8 of the time. That's a huge advantage. Even in Vegas, you're not at that big a disadvantage in any game. All right, now this is the easiest case. If you analyze any of the other patterns, I mean, tails is the same. I would pick heads, tails. Again, winning 7/8 of the time. Those are the 2 easy ones. Throw those out. All the rest of the patterns, if you sit down and analyze that pattern compared to the proper choice against it, they all give a probability of 2/3 for the proper choice. That's still a huge advantage. I'd like to play that game against somebody all day long. If I could have had that opportunity, I would have retired many years earlier. Okay? Now, what is the proper choice? This is the crazy part. The proper choice always turns out to be, we're going to select, the opponent selects their pattern, I move their first 2 choices to be my last 2 in my pattern, and then I fill in the first position, which, with the choice that does not give me a palindrome. It's stupid, but it works. Other than the fact that I've seen the analysis, I've done the analysis, how somebody figured out the palindromes, how Walter Penny figured this out, actually, I'm not sure unless he sat down and analyzed every choice against every other choice. Man, would that be boring. But that's the way it works. So with the heads, I move 2 heads to be my last 2. And I can't fill in with a palindrome because that would be heads. So it had to be tails, heads, according to the rule. And from the analysis, it's easy to see that that worked. The other ones are harder to analyze. I'm not going to put you through that. You just have to believe me, which my students never did. They say, show me, which was what I wanted them to say. Okay? Clear? Somewhat clear? Again, it's just another crazy game, but if you put some math into it, you can learn how to win. Years ago, I was asked to teach a discrete math summer class to middle school teachers in Atlanta. And I accepted. I did it. So for several weeks, I drove down, had a group of 50 middle school math teachers, and I taught them a whole bundle of things. And I would teach them easy games they could play with their kids, where there were strategies to try to figure out. Some of them ate it up and thought it was great. And one of them raised her hand and said, I don't want to use those strategies. I said, why not? She says, it wouldn't be any fun. And I said, winning is fun, lady. Just playing blindly is the fun. You like to lose? Let's play later. She didn't want to play later. Hard to understand that approach, except for the fact that she was forced into teaching math. She didn't really like it. She didn't appreciate it. It's a sad situation on the kind of teachers we have, in the middle schools especially, that I know of. I can see some heads over there shaking yes. Okay, questions on this now? On anything else that I've done so far? And I should probably call it quits here.
We've got 10 minutes for questions and comments, and Al, Padwa's going to take this mic around if you put up your hand.
The webcast will not pick up your voice unless you speak into the mic, so that's why we're sending
And
Al
I
around
will answer questions
with the
on
mic. And it
camera.
will help if Ron repeats the question too. Oh, and here you go, Al, and I'll get that.
Okay, you talked about the one person who studied math and then became a computer scientist. What do you perceive to be some of the insights from what you're doing now that may have fed into computer usage?
Oh, okay, that part's easy. Think of the internet. The internet is run by a large number of certain computers that pass everything along. So before anything gets to you, it has to pass through some number of other machines to go from one place to another. If I put a dot for every one of those machines and draw a line between them, if they're communicating, then I get a graph. And now what they would really rather have is the best way for the communication to go. Why route it through 57 machines if I can route it through 3 and get it where it needs to be? That's actually very much related to work I do. Standard question. There's loads of such graphs. There's a thing now called network theory that's caught on big. And they fundamentally deal with large networks. And they try to answer various kinds of questions in various subjects, from sociology to computer science to physics to math. There's all kinds of questions. One of my favorite graphs that's been brought up is the co-authorship graph with a man named Paul Erdős. Erdős was, in my opinion, the greatest mathematician of the previous century in terms of what he did. He wrote over 1,500 papers. He presented thousands of lectures, and almost every lecture that he presented was nothing but, here are problems we need to solve. And he didn't care who solved them. He just wanted them solved. And he offered money on many of these. And Voight Riddle in my department holds the record for the most money collected from Erdős. And he's proud of that, and he should be, because they were always hard problems. So and Erdős lived his life by just traveling around, constantly, visiting place to place and writing papers with people and moving on to another place. Luckily, I wrote 4 papers with him. I'm pleased with that. That gives me the Erdős number of 1. Okay. Somebody who wrote a paper with me but never wrote a paper with Erdős has an Erdős number of 2 in the graph, etc. And so over the years, I've had many people come to me and go, I want to write a paper with you so I can get an Erdős number of 1. So it's not good enough reason. Give me a reason. But that graph has been analyzed and analyzed because it's huge. He had, with 1,500 papers, he had hundreds of co-authors because he loved to work with people and he loved to spread ideas. He was really so influential that he got the communists in Hungary to allow him to travel when they wouldn't allow others. In fact, he then forced them to allow all Hungarian mathematicians to travel, or he wouldn't come back. And they wanted him back so bad that they allowed all Hungarian mathematicians to travel. Russian mathematicians still rarely go anywhere. And rarely does anybody know what they're doing. Or do they, well, they have access to all of what we're doing. We have very little access to what they're doing. Yes?
I think I remember that the Princeton guy that won the Nobel Prize in math in A Beautiful Mind used mathematics to predict conflict resolution.
I think you're right. There have been several mathematicians who won the Nobel Prize, even though there is no Nobel Prize in mathematics, usually because of the applications of their work to other fields. economics especially. Just a few years ago, there was another mathematician who got a Nobel for work he had done 50 years earlier. And it had big applications in economics. And that's what got him the prize. There is what mathematicians call equivalently the Nobel in mathematics. It's called the Abel Prize. And it comes with it's over $1 million. Depends on the conversion rates at the time. But it's given once a year. I never got it.
Isn't there a Fields medal?
There's still
The
time.
Fields Medal is a different thing. That's a medal, but that's awarded to somebody 40 or under for outstanding work early in their career.
There's a problem, I think it's called a traveling salesman
Yes,
problem.
that's a graph
where
problem.
the salesman wants to visit 50 homes and he wants the shortest path without ever.
Right.
How do you go about solving something like that?
It is fundamentally unsolvable if the graph is big, but there are algorithms for coming close. A friend of mine years ago was hired by an oil company who wanted to send ships out to their oil rigs in an efficient manner, and he ran his program, took him probably 5 minutes, determined the route, and got paid $10,000 for giving him the information. Nice job. He then later was hired by a bank in San Francisco to figure out the routes for the armored cars to visit and be efficient. And he did that as well. Again, it took him 5 minutes and he made a lot of money. It's essentially what's called an NP-complete problem. There's no known polynomial solution, but there are lots of ways to do good approximations.
What about UPS?
I don't think they have any plan for what they do. From what I have observed, that when the same truck comes onto my street 3 times in a day, I don't think they are exactly planning things perfectly. I should offer my services.
They're also trying to avoid left turns.
And they should.
Al? Thanks.
So you mentioned the prize, $1 million, give or take, for mathematicians under 40, yes?
No, not the million is for lifetime achievement.
Okay. It reminded me, some of you may remember Bobby Paul giving our chef lecture a few years back and addressing the idea, as those lectures do, of creativity in later life. And one of the things he mentioned and talked about was what I've heard, and I'm sure you have too, that people in math tend to excel when they're young. You know, that brilliant work gets done by younger folks, whereas, say, humanities people tend to excel in age. Do you buy into that? What's your, no, not, I mean, look what he's been doing, right? So where did that idea come from, do you think?
Well, it's certainly true that a good number of mathematicians burn out. It's hard work.
Yeah.
Thinking isn't easy. And that's what we do, sit and think all day. I have a favorite quote from Bertrand Russell that says, most people would rather die than think. And many of them do. And it's true. And I've seen a number of good mathematicians burn out. You just keep working and working. And at some point they go, it's not worth it anymore. And I have to admit, I've toyed with the idea myself at times. But I enjoy it. I enjoy the people I work with. I enjoy the travel that goes with it. That's what's helped keep me going. It's not that, I told the dean this when I told him I was retiring, that paper number 1 was a big deal. I was an undergraduate. That was a huge deal to me.
Undergraduate, wow.
Paper number 10 was a nice thing. I was still a graduate student. Paper number 50 was a big deal. I was here. Paper number 100 was my next target. That was a big deal. 150 came and went, and I never noticed. It just wasn't a big deal anymore because I was kind of used to it. And I had achieved the things I thought I could never achieve. So now I would do this because I have fun doing it.
Yeah.
And if you can't have fun doing what you're doing the wrong thing.
No one else gets emails like you.
That's true. That is very true. I get some really good ones.
And he's made it fun for us too, so thank you so much.